So before we get to a couple of sample problems, I wanted to discuss something that I forgot to mention in the previous video. So here's a little reward for those of you that watch both, and this is going to be on your homework, so you might want to pay attention. And this is about the advantages of having many slits, so many slits, and the advantage of having small slit spacing, so small d. If you have many slits, the advantage of that is that you have more overall light getting through that's able to interfere, and so this makes your fringes brighter, and bright fringes are easier to see, so that's a plus. If you have small slit separation, if you think about our equation d sine theta equals m lambda, as d goes down, you get small slit separation. Theta has to go up. So what that does is it spreads out the fringes, and that can be a good thing because they're easier to measure if they're not all crammed close together. It reduces your error if you're measuring bigger distances and all of that. Also, I don't know if I mentioned that we don't have an equation for the dark locations, and that's because these bright locations are so distinct and spread out. You know, say these are my bright lines on my diffraction pattern. The dark locations are pretty much everywhere except these bright locations, so we don't really calculate the dark locations. Alright, a couple of example problems. We've got a 2500 line per centimeter grating, third order fringe, blah blah blah. What's the wavelength? So again, my equation d sine theta equals m lambda is the only one we're using for these diffraction gratings. Now some of the problems will involve a little bit of geometry in addition to this equation, but we can handle that, right? Okay, so let's list the information we've got. We don't actually have d. Actually, I'll come back to that. We've got theta, nice and straightforward, 36 degrees. Third order fringe, that means m equals 3. And we're going to try to find wavelength. That's our unknown. And we've got this information here, which is not exactly d, because d is the spacing per line, not the lines per spacing. So d is the inverse of this guy, 1 over 2500 centimeters up here per line down here. And you can go ahead and do this division here, and you'll get 0.0004 centimeters per line, and then you could plug that in, but I'm going to show you a nice little trick to do. So we're using this equation here, right? And I could plug that in for d, theta, m, and solve for lambda, easy enough. But if I go ahead and solve this for lambda first, I'm going to have d sine theta over m. And rather than worrying about inverting this, sometimes it doesn't come out to be a nice round number, so to speak, like this. You're going to have a whole bunch of decimals trailing off. So sometimes you want to plug in, instead of d up here, you can just plug in this number in the denominator because that's like inverse d, right? So you could just plug in sine of 36, and then instead of putting this in the numerator, you can put this guy, the 2500, in the denominator, times m, which is 3, and you can go at it that way. Now this was centimeters, right? Actually it was inverse centimeters. So this answer is going to come out in centimeters, and it works out to be 7.84 times 10 to the negative 5th centimeters. And that's kind of ugly for a wavelength. We usually like this to be in nanometers. The conversion factor between centimeters and nanometers, let's think about that for a second. So meters to nanometers is 10 to the negative 9th. Meters to centimeters is 10 to the negative 2. So there's a factor of 10 to the 7th there. So this guy becomes 7.84 times, if we multiply by 10 to the 7th, and add that to this negative 5, that's times 10 to the 2nd nanometers, or 784 nanometers. And if that gets kind of confusing doing all of that, You could just convert to meters first, and then this would have come out as 7.84 times 10 to the negative 7th meters, or I guess we could have, at this point, gone there, and then could have gotten there the same way. Anyway, okay, next problem. Diffraction grating has 500 lines per millimeter. Find the angular spread. So this means the difference in the angles. We essentially want delta theta between the two bright fringes that we see. For the second order spectrum between green light of this wavelength and blue light of that wavelength. So we need to find the angle to each of these bright fringes and then subtract those two angles. So again, our one and only equation for diffraction gratings. If we're going to solve for our angle, you're going to have sine of theta equals m lambda over d, and then we take the arc sine of that. So just getting my equation done up front here, and then we can plug in whatever numbers we want. Alright, so there we have it. So let's start out with the green light is that wavelength. So I'm going to say theta to the green light is inverse sine. M, we're doing the second order. We should list this stuff out first, I guess. Anyway, to the wavelength there, 550. I'm going to go ahead and convert this to meters times 10 to the negative 9th, right? And then we're going to divide. We could divide by d, which is the inverse of this, or we can put 500 up here. Now this 500 is inverse millimeters, and if I want to get that to meters, because this guy here is in meters, I want it to be inverse meters, right? So since millimeters would be down here, normally on the bottom I would divide by 1,000, but if I'm dividing the numerator by 1,000 to get this to meters, that means I'm multiplying. Did I say dividing the numerator? Dividing the denominator. So that means I'm multiplying the numerator by 1,000. So this becomes meters. Units cancel out, which is what we want when we're doing a sine calculation. So we just plug in 2 times this times 500,000, and we get the angle to the green light is about 33.37 degrees. Then we repeat the calculation for the blue light. We've already monkeyed with our line spacing, so that's going to be the same. All we need to change here is the wavelength. Instead of 550, we'll use 450 times 10 to the negative 9th, and then we can multiply by the same 500,000, and this gives us an angle to the blue fringe of 26.74. Now I'm rounding these when I write them down, but when I actually subtract them, I'm using the full values from the calculator, as always. So the difference in those angles is going to be the green light minus the blue light, 33.37 minus 26.74, and that gives us 6.62 degrees of angular spread, and we are done. It's been a fun year. See you in advanced physics, maybe.